Welcome to Linear Algebra Part 2. In this course, we focus our attention on matrices. Matrices pop up in many ways and have many different interpretations, but in essence, a matrix is just a rectangular block of numbers. Its shape is determined by its number of rows and its number of columns. Here on the screen, we have a 2 by 3 matrix. Note the order in this expression, first the rows, then the columns. If a matrix has only one column, it can also be regarded as a vector. You have already seen some operations on vectors of the same size. You can add them or subtract them element by element. And we can do the exact same thing for same size matrices. Just add up the corresponding elements for each location. You have also seen scalar multiplication of vectors. Every element is multiplied by the scalar. Once again, this operation can immediately be extended to matrices. In this video, we will focus on a third operation, multiplication. This will be a rather different procedure that does not follow the same element by element approach. For vectors, you have already seen several products. There is the dot product, and for vectors in R3, you also learned the cross product. However, multiplication of matrices is based on another product you have already seen, the matrix vector product. Let us recall the mechanics behind this matrix vector product using our example. We have a 2 by 3 matrix A and a vector V in R3. The matrix vector product AV is the linear combination of the columns of A using the components of V as weights. So AV equals -1 times the first column of A plus 3 times the second column, plus 1 times the third column of A. There we go. We end up with a vector in R2. Note that this only works since the sizes of A and V are compatible. The number of columns of A is equal to the number of components of V. To extend this product to a matrix-matrix product, we modify V. Let's give it an extra column. We call it matrix B. To compute the product AB, we work column by column. The first column of AB is the product of A with the first column of B, now highlighted in red. This is just our old product, AV. Next, the second column of AB is equal to A multiplied by the second, green, column of B. Here we go. We have just computed our first matrix product. So, a matrix product can be computed using matrix vector products, interpreting the right-hand side matrix column by column. Note the necessary compatibility of sizes. The number of columns of A must be equal to the number of rows of B. What about the size of their product? Each column of AB is a linear combination of the columns of A, which all have m elements. So just like A, the matrix AB has m rows. On the other hand, the column by column computation of AB shows that A, B and B have the same number of columns. To make sense of the definition of matrix multiplication, let's give some meaning to the elements of our matrices. The table on the right-hand side of this slide contains a simple recipe for cake in its first column and for a batch of cookies in its second column. On the left-hand side, we display a table with ingredient prices at various stores. To ensure compatible units with our table of ingredients, prices are listed per gram and per egg. These tables can also be regarded as matrices. It's just a slight change in presentation. Their matrix product will help us combine the information in these tables, or matrices, in a meaningful way. First, note that the columns of the matrix A on the left correspond to the rows of B on the right, not just in number, but also in meaning and units, flour, sugar, butter, and eggs. Now, let's compute the first column of the matrix product. As we have just learned, this is a linear combination of the columns of A. The first column of A tells us the cost of flour at our 3 different stores. It gets multiplied by the 200 grams of flour for a cake. Together, this gives us a list of the price of the necessary amount of flour at the 3 different supermarkets. So, as already suggested by the colors, the rows of our new matrix are still related to the 3 different stores. The second column of A contains the price per gram of sugar at our 3 stores. This column is multiplied by the amount of sugar in our cake recipe. We obtain the 3 possible prices to buy the needed sugar. Likewise, 200 times column 3 gives us the price of the butter, and 4 times column 4 the price of the 4 eggs. Adding all this, we obtain a vector in R3 that lists the price of the cake ingredients for each of our 3 different stores. The second column of AB will give us the price for a batch of cookies. The matrix product gave us a price comparison table for our baked goods when you buy the ingredients at different stores. However, we do not have to perform this computation column by column. Instead, we can zoom in on a single element. Let us consider element 3(2) in the matrix. As visualized by the colors, it combines the prices at store Z, listed in the third row of A, with the ingredients of a batch of cookies, listed in the second column of B. We buy 300 grams of flour at 0.19 cent per gram, 200 grams of sugar at 0.08 cent per gram, 100 grams of butter at 0.97 cent per gram, and 1 egg for 39 cents. Summing this, we find the price of ingredients for 1 batch of cookies bought at store Z. Similarly, the other entries of the matrix product list the price of ingredients for a certain baked good, the column, at a certain store, the row. The matrix product performs the computations needed to fill in our new price comparison table. We have just obtained a second way to compute a matrix product, element by element. The entry at location I, j can be computed as the product of row I of A with column j of B. This perspective may be convenient when you are only interested in some particular entries of AB. Let's return to our cake recipe slide. Its colors can help us find a third perspective on the matrix product. There is a pattern in the construction of the rows of AB. For example, note that row 2 of AB can be regarded as the product of row 2 of A with the entire matrix B. To get the prices for our baked goods at store Y, we need the ingredient prices at store Y and both the recipes. Prices at other supermarkets are not relevant. In fact, row 2 of AB is a linear combination of the rows of B, where the weights are the elements of the row 2 of A. Row 1 of B, the flour in the recipes, is multiplied by the price of flour. Row 2 of B by the price of sugar, and so on. So why do we want to look at this computation in so many ways? Because depending on what you want to do and how you interpret your matrix, one view might be more helpful than another. And we need these shifting perspectives in the remainder of this course. Before we end this video, one word of warning. The order of these matrices is irrelevant. In this example, the product BA is not even defined, since the number of columns of B is not equal to the number of rows of A. And for matrices where the product is defined both ways, the outcomes may be radically different. Okay, so we have defined a product for matrices. I encourage you to take some time to practice this computation. Then we'll take a look at the properties of this new concept. After all, we have already seen that some rules that work just fine for products of numbers are not valid for products of matrices. See you at the next video.